So we welcome every one of us to today's presentation. We'll be talking about continue with what we've started. Then today we'll be talking about the random forex and some other analysis. Over to you, sir.
So, is it displaying now?
Yes.
Okay. All right. Good evening once again. Well, we are looking at this evening. We are going to be looking at decision tree, and we are going to be applying R to obtain some results. The outline is as follows. You look at the introduction section. You look at the structure of the tree. We interpret trees, improve decision tree prediction, talking about bagging, random forest, and boosting. We are going to be talking about pruning and fitting trees. We will also discuss random forest versus support vector machine. Then the data set we are going to be using is Boston data, cassettes. Then look at exercise and the reference. Now, decision tree, as the name implies, is very flexible. The trees are flexible, and as a machine learning models, it solves both regression and classification problem, and you can use it for both categorical and numerical predictions. This tree I'm talking about is very flexible to interpret and is accurate and stable, and there are rules that guides the making of a tree, just like a flow chart. Okay, now each decision or split is represented by the branch, just like you have a branch of a tree, and the root node contains all the data in the population. Now, in a tree, when a given statement is true, the left split is selected, and if the statement is false, the right split is selected, unless other state otherwise. And usually drawn upside down with the trunk at the top and the branches in the middle and the leaves at the bottom. When we talk about classification tree, we talk about the dependent variable. The dependent variable is categorical in nature if it's a classification tree we're talking about. But in the case of regression tree, the continuous variable is dependent. Now, let's quickly look at the structure of the tree. For a given tree, you are going to be having the following. The root node. It contains the entire population of the data before division occurs. Okay. Then the decision node. These are intermediate nodes or subnodes that are split into further nodes. The terminal, as the word implies, if the tree is no longer going further, the decision will be made at a point. At that point, that's why it's called terminal node. Then the branch, like you have in a tree, the parent and the child nodes are divided into decision or terminal. You either terminate or go further, just like you have in your flowchart. So the top level node is referred to as parent node, while the subnodes are called the child nodes. Then the splitting, that is a recurring process of dividing the population of a node into two subpopulations or nodes. Then the pruning is just when you decolorate, when you cut down the branches. Okay, you remove the subnodes from the decision node, and you can see that it actually is opposite of splitting. And the reason why we prune is just to avoid having a complex tree, which will result into overfitting. So the fewer, the better, and the variance will also be reduced. That is why pruning is necessary, okay, to avoid having a complex tree. Now let's look at what the decision tree looks like. We start with the root node, then the branch decision node, You look at it at the left, the one that goes to my left here, it terminates at the point. The other one that doesn't terminate, you are still going to continue with it, which means at the point to that one to terminate. All right, the one on the right, you have the decision node, then it terminates at the point. You can see the child node there, and the parent node is where that point, that decision node, knows the parent node. Now let's look at this tree. I want to interpret this tree. Like I mentioned earlier, that the one that goes to the left, it actually terminates at the point, but one that goes to the right, the process continues. Now let's look at this, let's interpret this tree. Assuming that X represents age. Now what it's saying is that you can see that the regression tree starts at the what? At the root node over up there, and is split into two subnodes, depending whether X is more or less than 29.5. Okay, so the subnode to the left, you can see now, if X was less than 29.5, then you split. Are you getting it now? Okay. We split into two nodes again, depending on whether X1 is more or less than 21. You can now see that point. If X is less than 21, the prediction will be what? 42.311. And if is less, otherwise, it continues. If X is more or equal to 21, the subnode further split into two leaves. And those are the two leaves we have there. I hope you are following. So it splits into what? Two leaves. So you can also, depending on whether the person is older or younger than 16. If the person is younger than 16, the prediction is what? Is 40.231. But if the person is older, is 35.5212, as we have there. If X is more than 29.5, that is the one, the upper one. We have dealt with the left part now. We are now going to the right. If X is more than 29.5, the root node split into two nodes. And that is a function of whether it's greater or equal to 35. If it's less than 35, the prediction is 29.5. You can see it terminates there. If X1 is more or equal to 35, the subnode split into two subnodes. That is, you can see the 40, less than 40, greater or equal to 40, you can see on the right hand side. If X2 now is less than 40, the prediction is 51.3221. And if X is more than 40 or equal to 40, the prediction is 64.6121. And that is just for the regression tree. Now, let's go to the classification tree now. In classification, like I mentioned earlier, for classification, we have, like I mentioned, the regression, we have continuous terminal, whereby in classification, it's categorical. So let's see. Now, looking at this age at the center, so the data is now split into three categories in this age. We have the students, we have middle age, and we have senior citizen. Assuming we make the student to be someone that is 30 or younger to be that youth, then somebody that is 55 years or younger, probably we say 55, you can say, okay, middle age, then above that is senior citizen. So, as a matter of fact, actually the data sets was continuous, but we want to make it what's it called, categorical now. That's why you now split into different categories: youth, middle age, and senior citizen. Okay. Now, like I mentioned earlier, I said if the person falls into the youth category, the node split into approve and decline based on whether the person is a student or not. You can now see. You can see students there. If it's a youth, we will now split. Whether it's a student or not a student. If it's a student, you can see the right-hand side, approve. If it's not a student, you decline. You can see. All right. If the person is middle-aged, the prediction would be to approve. You approve. If the person is senior citizen, the node split into two subnodes. We can see there. Depending on the person's credit rating. Fair or excellent, you can see, is either fair or excellent. If it's fair, you decline. If it's excellent, you approve. So that is what this decision tree is telling us. Okay. Now, we can see that in the regression tree, the terminal nodes are continuous, whereas for classification, the tree are categorical, just like we have in this illustration. Now, let's now look at interpreting tree, which I've actually talked about this because I don't want to scroll here while the, what's it called? The tree is on the other side so that we can see it properly. Now we have talked about terminal nodes. How do we improve trees? Like 3 ways to improve tree is bagging, random forest, and boosting. Now let's talk about bagging. In the case of bagging, we select from a training data set, we select some training data sets. Let's say we have the first one, the first training set of data that we have gathered is F1 cap, F2 cap, up to B, into B separate training data sets. This is to be done in order to reduce the variance. So you know what bootstrap means? Bootstrap means sample with replacement. Now, after doing that, we now average it, and that is what we call the bagging process. Now, some of the data that is not used is called out of bagging, or out of bag. So, assuming we use three-quarters of the data set, 1/3 is out of bag, and it can also be used to estimate prediction out of bag error. Okay. Now let's look at random forest. Random forest is actually similar to the bagging. What we want to do here is just a small tweak, and it's just to decolorate the trees. Now, bagging and random forest, what differentiates bagging from random forest is that the end predictors, the subsets, the sub predictors, is the same thing as what? The P. So we use the full predictors in the case of bagging. But in the case of a regression tree, we use P/2. We divide it into 2. But we are talking about the classification. We take approximately the root of the P to be our predictors. Okay. So, what differentiates bagging from random forest is a subset M. Now, boosting. Boosting is actually similar to bagging, but the difference is that the trees are grown sequentially. Okay, so each tree is grown using information from previously grown trees, just like the Markov chain. So, boosting does not involve bootstrapping sampling. Instead, each tree is fit on a modified version of the original set. So, and boosting can overfit if B is too large, talking about the sub. Okay. Now, the training, different set of training sets. And we actually select our B using cross-validation. I think the first class we talked about cross-validation. Now, we also use what we call shrinkage parameter, just like we have in the case of lasso and reach. So a very small lambda can require using a very large value of b in order to achieve good performance. And we know that the lambda also controls the rate at which the boosting learns. Now let's look at fitting and pruning trees. Now, if you want to prune tree, like I mentioned earlier, to avoid overfitting or growing complex trees, we have to prune the tree. Okay, and you can see that we have our T, which is the subset of the entire large tree, which is a T naught, and we can see that our alpha, which is likened to, you can see that alpha T is there, which is likened to the constraint or given in the case of lasso or penalized regression. And we can see the number of subtree, the number of subparameters, and we have our the Q subscript M of T, which is actually expressed in the formula there. Okay, now we can see that this can be obtained. For further information, you can check James et al. 2017. Okay, now let's look at I want to talk briefly about the difference between random forest and support vector machine. And this happened to be an interview question for a data scientist. It said, give some situation where you will use support vector machine over random forests. Vice versa. That is, these two procedures, they have their strengths and weaknesses. But this question is now saying, when would you rather use random forests and when would you rather use support vector machine? Let's look at the two. Now, it is easier to train a well-performing random forest classifier since you have to worry less about hyperparameter optimization. Don't forget that last week, we talked about the support vectors machine, and we talked about the hyperparameter, the optimization condition. So in the case of random forest, it is easier to train it. You don't have to worry yourself about the hyperparameter, about and some other things. Okay. Now, another reason why random forest is preferable is you are less likely going to overfit. Okay. Another thing is that you simply grow M trees on M bootstrap samples of the training set on feature subspace. Random forests are more automated and thus easier to train compared to SVM. You can see the reasons now. Now let's now look at the strength of support machine relative to the random forest. Okay. Now using support vector machine, you have more things to worry about, like I mentioned before. Okay, talking about choosing the appropriate kernel. Last week, we talked about the radar kernel, the linear kernel, the Gaussian kernel, and the rest of them. So, okay. Now, let's look at the second point here. There are many examples of SVM, where SVM perform random forests on different data sets. So if you like to compare these two, make sure that you run a large enough grid. You have to do a grid search. Before you actually fit it, you have defined your grid. Your grid can be as much as 10 million. Are you getting me? Which you include in the training process. All right. To reduce the performance estimation bias. So you can see the strength now. Above it all, it appears that random forests outweigh SVM in a way, but it depends on the type of data you are using and the features of the data set. Now let's look at, to illustrate what we have been saying, we look at a data set built into ISLR package. It is called Boston data. Now, the description is the data set contains 506 rows and 14 columns. Okay, now these are the parameters. I think they have 14 parameters. ZN, proportional of this, IN, chase, and all. You can see all the different the median value of owners occupy owned $1,000 black. That is talking about a proportion of black by town. Health stats, lower status of the population in percentage, and some other things. So by the time you look at we put it into work, you'll be able to understand which data, which variable is important and why we use them. Now let's look at the data set is in mass actually. Now to do that, we call our library mass. We also talk about the library, the package tree. Set seed is equal to 1, like I said, set seed is just to create initial value. Then we train it. When we say sample into all this, simply means we want to use from 1 to number of rows that contains in Boston data. Then this is the size. Size is half of it, which is 506. 506, that's what I'm talking about for the training. By implication, what you're saying is that 50-50 training and testing set. Then the summary will say what it looks like. Then the next thing we do is to grow a full tree. Okay. Now, after growing a full tree, you can see what a full tree looks like. Okay, this is the full tree. Then after pruning. Now, like I said earlier, I said we select our the parameter, which is alpha here, using cross-validation. The cross-validation tells us that you have to use 4,000. So we can now see how this complex tree has been reduced to what? To this a very simple tree. And how do we interpret this? This particular one, it was fitted in R and is one of the examples provided in the study exercise, in study material in the University of London. So I adapted it from there, and actually it's provided in R. So now look at this example. Look at what it produced. How do you interpret this tree? Now we can see that we want to, don't forget that, let's look at our variable here. Look at the variable. MDV, median, what's it called? What's our MVD? Median value of owners occupied homes in $1,000. So what we are predicting is actually the median price. So how do we interpret this tree? Now, the median price of homes in areas with average rooms less than 69.41. What we are saying there is 7, actually. There's no 69 number of rooms like that. So we are saying 7. And less than, look at this F stats, mean economic status. Now, percentage of economic status, and less than 14.4% population in lower economic status, that's a variable, is this $23,350. You know, is in thousand, we multiply. So that is what for lower, you can say. So the above price drops to 14.960 if population in lower economic status is higher than this. You can now see it drops. The left-hand side simply means less. The right-hand side in the over there is meaning greater. So, and that's what it means. Now, this can further be saying, when you look at the right-hand side from the node, we can see that the one that goes to the right, just the median price of homes in area with average rooms more than 16.9 is this. So it terminates there. So that is for that. But probing further, I now used K to be equals to 3,000, and it's alpha. Now, I now have additional, instead of having just terminating at that point, you can see additional, the extension of the right-hand side is now there. Now, the addition is that, well, let me just read the last 2 lines. It says, the median price of homes in areas with average rooms more than 7.437 is 45,100. The above becomes this 32,110 in areas with average rooms between 69.941 and 7.437. You can see that this particular value falls between the RM above and the RM below. And that's why it's interpreted as thus. So let's now go to the pruning. This is the what was it called? The code, R code used for the pruning. Now, cross-validation was conducted, and the K there was using K equals to 4,000, and that was chosen. We prune. When we plot, it won't give us those values. When we now put text prune dot Boolean, it brings out the values in the tree. Then we now use the prune tree to predict. When a prediction was done, our MSC is 29.9040, and the square root of that is 5.468. Okay, now we can see indicating that this model leads to test prediction that are around 5,468 of the true median home value for the suburb. Okay, now let's look at Bayesian and random forest. Now, for the choice of the code for Bayesian and random forest, what differentiates them is just if they are the same function will produce them. Like I mentioned earlier, when you are doing classification regression problem, we divide it by 2, and we have we are using all the 13 variables as our predictor, and you can say 13 divided by 2 in the case of random forest will give you 6. So approximately we use number of variables predictors there to be what, 6. Now let's look at the left hand side, which is the Bayesian. In the Bayesian, we use the full predictor, and we got 13.5141 as our mean square error. Now, when we now use the random forest, you can see that it has dropped. The MSC has dropped from, so you can see that the random forest is an improvement on Bayesian. So that takes us to the relative influence statistics. We can see here that, look at it, from the plot, L-stats and RM happen to be the most important variables. Look at how large they are. L-stats, RM, 37.066, 25 points. So what actually determines median, what is it called? Median price of homes in the area is determined mostly by people living in low economic status and number of rooms. So followed by DRS, and so that's how they follow based on the statistics we have here. Okay, boosting. We now do boosting. We can see that we can't use the function of random forest for boosting. Rather, we use GBM. And that will make us to install a package called GBM. So we call it after installing GBM library. Then we have our set C, then we proceed. You can see the first line GBM, MEDEV, and we have our data as boosting. We have our training set, and then depth. Our depth was chosen to be 4. Why do we choose? Why is depth important? Depth tells us how many split a tree can make before prediction. So you determine how many trees you want to make before prediction. So, and when we use boosting, you can see that even boosting actually further reduce the MSC. When we get to the lab session, you are gonna see all this. Now we can also do that, like I mentioned earlier, we can use our shrinkage parameter, which is the default is 0.001, but you can choose your own shrinkage parameter lambda and see what the output will be. Now let's go to cassettes, another data set called cassettes, and that one is taken from ISLR package. You can see the variables here: sales, advertising, income, price, urban, education, age, shelf, block, and all. So we have our cassettes. To turn the variable there, the sales, to turn it to categorical, we can just change and say, okay, anything less than equal to 8, we say no. Anything greater than that is yes. So that's you can see the first line using if-else statement. Then we have our data frame, cassette, then high, if it's high, and it is low. So we have we fit it as factor, then we obtain our tree from there. All right. So now we split. Now let's go into the regression now. We split this into training set and testing sets using create data partition. To do that, we need correct package. We have created the training set to be 0.8 of the data set, which is 80% of the data set. Then it tests the remaining 20%. Then we fit our tree as does. Then we plot and we obtain our tree. Now, but we have to, before we do that, we have to, before we obtain the tree proper, we rely on the cross validation. Now, in the cross validation here, we have the best. We have to choose our best. I think the one with the least what was it called? The size here, we can see 7. So we choose 7 to be our best. You can see where it falls. It falls between just after 5, then 6. Someone can say 6, but I think it's 7. Then we now plot our tree again based on the cross validation, and we obtain whatever it is. We'll see it in the lab session. Now, we want to predict now from the prune tree, and we follow this particular command. Then we have this output. Then we produce a conversion matrix is also produced. Now, I just screenshot the R, and the output is as does. You can see the accuracy is 74.79. You can see the confidence interval 0.601 and all, and other parameters, other estimation, other statistics produced. So, and these now for the Urban, we are going to use Cas6 data set, and we use Urban as response variable to obtain the MSE for bagging, random forest, and boosting. Then we comment on our results, because it was not done for this particular data set. So it's an exercise which you are compiling to submit already. For those that have not submitted, this is the 4th one. Okay. If there's no question, I can now go to the lab session, which is the RStudio. I believe you have launched your RStudio already, so that we can follow as I do it.
Hello, Doc.
Yes, please.
Sorry. Can you do us a favor by go through the interpretation of each of the results?
Which of them?
Now we talk about from the random forest. Yes, from the first one, where you are interpreting the results of the graph. Yes, this one.
Okay, of the chart. Okay.
Yes.
Of the plot.
So,
okay.
How do we, when we have our own data, how do we interpret it?
Yes.
What are the things do we need to be focused on? Based on this data, that's why you can interpret. Is there a particular, are we talking about when something is less than alpha, when this is less than A? Is there a particular, like between 0 and 1, anytime you have this is what it simply means. So I want you to share more light on that before we move to R. Thank you.
Thank you. If you are fitting a regression tree and you give instruction to plot, the output will be this, something like this. This already is a prune tree. So if the output comes based on the data you have, the med v, which happened to be the response variable, is the one. That's what you are trying to work on. So we want to predict the median price of homes in that area. So, and the predictors there, room, lower economic status. Having seen this tree, what will come to your mind is that these are the 2 variables provided after the tree has been pruned. So And the one that goes to the left is telling you less, as the sign implies. So when you go left, the next thing you see there at the what's it called now, the terminal node there, you can see that lower economic status is there. You can see this child node, low economic status is there. Okay, now that tells you that is in percentage from the data set used, is in percentage. So that will now inform what will be the next thing. And don't forget that when it terminates, it's actually telling you that the that is the median price, because that is what we are actually predicting. That is what we are predicting. So when it terminates there, it gives you the prediction already. That's the median price. That's the end product, the baseline. So this first one is okay, 6.941. It branches to the left. And it's saying that the median price of homes in areas with average room less than 6.941 and less, we already have one less up there, and less than 14.4% population in lower economic status, it will give you this particular price, $23,350. Now, can you see now? So the median price will now drop if the population in low economic status is higher than 14.4%. You can see that the one right hand side now, if it's now what? Higher than that. If the percentage is higher than that, than 14.4%, then the median price will drop. So for the one on the right hand side, it's just telling us point blank, if the median price of homes area is more than 69 point, which is approximately seven room, that's the price. If you have 7 room and above, that's the median price. It will be 37.24, in thousand. So that will give you 37.240, I think. Okay. So 240. So that is the interpretation. Okay, because we know where we are coming from. What the point is to predict the median price of homes. So whatever you do, any value you see at the tail end, they're actually the prediction that is being sought. Now, in the case of this, now you can see there's an additional branch there. So, and the interpretation follows the same. Can I proceed to the any other question, please?
You can continue.
Okay, so I can go to the lab session now. Okay. Yes. So now the first thing we talked about on the slide is the Boston data adapted from mass package. So we also need library tree. Without that package, the tree will not form, will not produce, the tree will not be produced. Then our set state is 1, line 3. Then we train the entire data 1 to 506, comma size, which is half of it. So 50% for training, line 5, 50% for testing. So let's now have it. I can now, okay, if I run this particular line 1 and 2, I have what I'm doing there is calling my the libraries that I want to use. Then set.seed, that is the initial starting point. Train, if I have my train, okay. So, okay. So based on, okay. Now, the summary statistics being produced based on the training set. So what it's telling us is that for the analysis, we're going to be using number of room, L-stats, frame, and age. I can't remember what frame means anyway. So now, like I said, we grow the full tree, which is if I do line 10 to 12, the tree should be produced. Okay. All right. So this is the full tree now. If I didn't put this text into tree.bootstrap, it won't give me the values there. So this is the full tree that we have grown. Then we prune it. Like I said, the K was obtained using cross-validation using 4,000. So I'm doing line 15 to 17 to see a new tree after being pruned. So this is the tree I just discussed. Like I said the median price of homes in areas with average room less than 6.941 and is less than 14.4% population in lower economic status. That would be the median, 23.35. Otherwise, it falls to 14.96. So that is the interpretation of that particular tree. Then the next thing I'm going to do is to use the prune tree to obtain, let's see, let me do up to 22. Okay. So this is what we have. Then a blind. Okay. Now this is you can see what the prediction looks like. Some of the points don't actually fall on the line. So we want to see what our the MSC looks like. Then we run line 24 is 41.2204. We can see now that when I did it, I got 29.904. So if this thing changed, it changed. So the value changed. However, what we now do next is to obtain the square root of that, which is root means square. We obtain the square root of that, and this is what we have. 6.420. Okay. Right. Now, as explained earlier on the slide, instead of using 4,000, I use 3,000 to see what my tree will look like. Then I have this tree. Well, so you can see what I have now. And that is what I said earlier by talking about the last two lines. I said, look at it. The median price of homes in areas with average rooms more than 7.437 is $45,100. Okay. it will become 32,110 in areas, dollars in areas with average rooms between 7 and, it's actually close. So let's just put that 6.941 and 7.437. No, rooms cannot be that valid, but so that's just what the prediction, that's what the interpretation is like. Like I said, you start with the data set that you have obtained. Then based on the data set that you have, you code accordingly, then you obtain your results. And this is what the results is like. And like I said earlier, this tree method is stable and reliable. And it has been proven to outperform some other techniques. So once you get it, you will find whatever analysis you want to do very convenient and without stress. Now, let's look at bagging now. I mentioned bagging the other time. In bagging, you use M equals to P. That is, the entire predictors will be used as a subset. And the same function you use for bagging, you also use for random forest. So the random forest function holds here. So let's go to, to do that, we need our library random forest. We call our library random forest. Okay. So we have it now. Then we have our sets.set. We have this. So we are fitting it on all the 13 predictors. Okay. Okay. Then we want to predict now. Predict. So line 39 to 41. And it's running. Okay, so we can say that this actually looks better. You can see that most of the line falls cluster around the straight line. Then let's look at the mean square error, 23.59 as against 41.22. You can see that is lower. Now let's now look at random forest. Random forest. In random forest, like I said, we use our subset is P over 2, which is 13 over 2, approximately 7, 6 or 7, whichever one you choose. So we run line 42 to 44. Now that's the prediction. If I want to say, if you now say print this now, y at, you see the lot of it will be so much, but let's now look at our prediction now, our MSC. We can print that one, maybe on your home, print it so that you see what results will look like. 19.6201. So you can see that it's still an improvement. The random forest. Now let's now proceed to the boosting. The boosting. In the boosting, I said you are going to need package GBM. So we call the package that already installed in the library GBM. Once we call it, we have our set seed. Then we have, let's look at it. GBM is our function. So our depth there is 4. What we are saying is that the splits that we want before prediction is made, Then we have our summary. So okay. Okay. Now, like I already explained in the slide, that the most important, you can see even that claim, okay, 43.33.12, you know. So the two most important, they can see the difference now. It's actually outweigh every other variable there. Is number of room that determines mostly the median price. Okay. Then percentage of people in lower economic status. So those two variables are powerful in predicting the price, the median price. Okay, now let's look at the prediction now. I'll run line 54 and 55 for the prediction. You have 18.84. You can see the difference is clear. From 43 to 23 to 19 to 18. Okay, so okay, if you want to use the shrinkage parameter, let's use 0.001, like I said before the other time. You know, we can further include a shrinkage parameter there. And I use 0.001. Let's see what that one will give us. I don't think it improves anything much. So you can see that it's still high. So you can be varying the parameter and see which one will outperform others. But this one is in between the random forest and that of boosting the value here. So using is still boosting, but with parameter with lambda, which is a shrinkage parameter. So with this, I can say we have come to the end of today's section. If you have any question, you can ask. And you have contribution to is welcome. You have our faculty members here. And also we have something to say and participants. Thank you. Doctor, okay?
Yes, sir.
Yes, so over to you, sir.
Thank you so much, sir. The question I have, let me quickly ask a question here before when we are saying, is there any difference between bootstrapping and boosting?
Yeah, bootstrapping is actually sample with replacement. You sample from the training set of training. You have data set, partition them into different data points. You know, maybe like you have 20. You partition them into 20. You partition, you remove maybe like 50. You put it aside. Another 50, put it aside. So you now train them. Are you getting me? So they are training set actually. Then
Okay.
you bootstrap them. And bootstrapping is actually sample with replacement. You sample, you replace, you sample, you replace. So for the process of bagging, that is where you consider the process of bootstrapping. Then you average what you have bootstrapped from the set of training sets that you have partitioned, you have extracted from the whole set.
Oh, okay.
So
okay.
that's just it.
Thank you so much. Do we have anybody with any question, please? We have any question you want him to explain something that is not clear to you, kindly wave your hands. Just raise up your hands or put it in the chat. Please, let's ask question now. Should we say the silence means it is clear? No question. If you said no question, Dr. Dare Julius, do you have any question for us? Obo Samuel, any question? Mercy Oladapo, Ajayi today. Okay. Then where again can we use this in industry?
Wow. Well, even these data sets that was used, it could be a what was it called? A housing data set. Maybe people in housing.
Okay.
You know, you can see.
Those in property management.
Property management. You can see. You can even see that they even have black. That means race is also part of what the economy. You can see low cost housing now. What can determine? Okay, how much low cost housing do we need in this particular place? You collect data. Then
population.
How much should we charge them? What can they afford? What is their salary like? You know, so the things that inform. So you can decide to use this approach if you're in any, even in banking, anywhere, even in my biology is applicable.
Sorry, sir. Is it possible to show us the data set? Can we see the data set?
Okay, this data set.
Let's see the data set. Probably it will help the heading. Will help us.
This data set.
Good.
You said sales, price, income, advertising, population, price. That's for the boosting particularly. This is not for CASIT actually. Age, education, urban. Yes. You get so that's
okay.
But for the CASIT, we can say okay, age. We can see what it looks like. Age, CASIT. And you know, in the slide, the variables were actually outlined in the PowerPoint. So
the spelling of CASIT is not correct.
T is missing there.
T, yes.
Okay. So we can see sales, price. Okay, this is also CASIT. This is CASIT, Boston. Okay.
The one of Boston is different.
Yes, it's different. It's different. Let me see. It's Boston.
I think this one is talking about crime.
Room, age, all those variables. They were actually explained in the PowerPoint. You know, black, whether if you are black, if you are this, median, price, something. So the tax, all those things were explained there. So it's not limited to, you can use it, you know, like I said, there's classification, there's also regression. So it depends on what you are doing particularly.
So basically, can we say that which one, the classification is the tree diagram?
No. We have classification tree, we have regression tree.
Okay.
Classification is when, do you understand now?
Yes.
When the response variable is categorical. You know, like I said, they say age, you say youths, middle age, and elder, what they call them?
Senior citizen.
Senior citizen. They have been classified, they have been categorized. But initially, before categorizing them, age is just age. Are you getting
Yes.
it? So now, that is when we use the classification tree. So it's the same tree, but their node differs. So that's just it.
Any other question, please? Dr. Adegoke, are you there? Okay, Dr. Dare, over to you, sir.
Good afternoon.
You are welcome, sir. Go ahead. Please ask your question.
Good evening, Prof. I really appreciate this opportunity, sir. And I want to congratulate our Prof.
Dr. Adeshina, can you hear him?
No.
Please, we can't hear you. Dr. Dare Julius. We can't hear you. Okay, we have a question here. Must we always set the seed to 1 from the onset of the code written? Can we always get data sets for all kind of work we are working on? I know that one. How do we know if data set we need is in ISLR?
Okay. Yes. Let me start from number 3, 2, 1. That order. How do we know this? This data set we are using is just for illustration purpose. Don't forget that the first day, you can also write, I saw how to write from R into Excel. You can pick it in Excel and use it if you anyway. But the point is that this is just giving you the structure of your data. Should you want to use your data, just check with the data that is available to you. Then, if you want to replicate that same thing using your own data that you have obtained, then you can use this for illustration purpose, actually. So you just for illustration. You could use any data set that is compatible with this. Okay. Now, can we always get data set for all kinds of work we are working on? Well, actually, yes. In every package, there are data sets there. If you want to know data sets in a particular package, you can just go to what's it called now? Go to the R session and just check the libraries. In the libraries, you will see some of those data sets available there. And any package you are working with will also guide you. You go for the PDF of that package and check the data sets they have in that package. You can now call that data set for use if you need them. Now, must always set the set seed to 1. Okay, well, like I said, the 1 is just the initial value. You can use 1, 2, 1, 2, 3, 1, 2, as the case may be. The idea of using the set seed is just for you to replicate that same result anytime you want to do it again. That is the importance of, you can as well do without the set seed, but it's advisable to just use it so that you can replicate that result whenever you want to do it again. So I think that's clear.
Thank you so much. Yes, Oja, over to you.
Okay, thank you so much. Wonderful delivery. Thank you, Dr. Lumide. I'm Femi Ayola. Have been very much attentive. As you said, let me start from the last statement you made there about setting seed. So for the seed, We can put anything there. We can set anything there, right? It could be 2, 3, 4. It could be 1, 2, 3. It could be 9, 10, 11, 12. You can just put something. Why? You set seed in order for you to have to be able to reproduce your result. It's an interview question. Why do you set seed? We set seed for the sake of reproducibility. We set seed for the sake of reproducibility. If you don't set the seed, because your number are random, each time you run it, you'll be getting different results, different parameter, different estimates. So that is all about that. Where is it useful? This concept that our professor just taught us, it's applicable in all human endeavor. In industry, currently, when it comes to stress testing, because we know that the economy is not really stable. Look at the inflation everywhere, all over the world, right? And that poses a lot of stress into the economy. So you can use it in the areas of a stress testing. You can use it in the area of a validation, right? You can use it in the areas of a model development. You can use it in the areas of a parameter recalibration, when you needed to recalibrate your parameters to see whether it's actually capturing the effect. Because the model, as we have the production model, so we have a theoretical model. So you can make use of what our professor have taught us in all spheres of life. That is my contributions towards that. And in addition to data, as he said, once you get to wherever God is taking you to, you have more than enough data to work with. But this basic approach is what we must just adhere to. We must know this. Once we know these step 1, step 2, as they are taking us through, and we still make all these notes available to ourselves, because by then, of course, Google will be of your friend. There's no way you'll be a data scientist without having it. Of course, I'm privileged to see both academics and industry. What we do in the area of publications in academics, it's theoretical with a very few data. Of course, I've simulated in the areas of academics with about 1 million tables. But I'll still tell you that data is still very small. Coming to industry, you will see mass data. But the moment we are able to master what they are teaching us here, we keep this note, it will always propel us and help us through whatever we may be going through. Thank you so much to the organizers.
Thank you, sir. Thank you, my boss. God bless you, sir. Any other?
Thank you. Thank you, sir. Yes, Dr. Dari. Over to you. You can unmute yourself.
Good evening over there.
You're welcome, sir.
I really appreciate our prof in the house for this insightful presentation. I just want to plead for one thing. For some of us that did not start with the prof when he started. So I would want to plead that, if possible, if the video can
okay.
For some of us to, but the one I came over halfway. So I'm just pleading on behalf of others. So
okay,
thank
no
you
problem.
very much.
What I will do as we're talking now, I will just upload one of the video. From that video, you can get others. So I will upload one of the
okay,
videos.
sir.
From that video, you can get others, and from then, yes.
Dr. Okay, are you there?
Yes. I just uploaded I just put the link on the chat now. Just click on that link. The YouTube link will take you to the channel where all the videos are. So we can easily walk, we can easily follow.
Please mute your mic.
Can you hear me now?
Yes, I can hear you.
So I've in the chat now, if you check the chat, you will see I put the link of the YouTube channel where you can just click and download or watch all the previous teaching. Any other question, please? Question, contribution? Okay. Any other contribution, any other question? Now that we know what the seed, where we said the seed equals to 1, what it means, and how do we handle industry data sets, I think the more you practice, the more you know. On this note, do we have any other contribution? Dr. Adegoke, are you there, sir? Ogusanya, are you there, sir? Okay. Dr. Adeshina?
Yes, sir.
So any other information before we call it today? Okay.
Okay.
Dr. Ogusanya, do you have any information for us?
No, sir. When our professors have spoken, what else will? I think I'm okay. I'm okay. On a lighter mood, I'm okay.
Okay, no problem. So please help us inform the Python people, guys. You should get set. We are rounding up very soon. So
okay.
Thank you so much.
Dr.
Adeshina.
Yes. Next week, hopefully, slightly good. We are looking at unsupervised learning. So we'll be looking at it and the cluster analysis and the rest of them, the hierarchical clustering, the k-means clustering, and some other ones. So, and if time permits, we look at the principal component analysis as a form of unsupervised learning. And for next week, by God's grace. So have a blessed weekend.
Okay, thank you so much. And to everybody, every one of us that have made it possible today, we want to say big thanks to you, Professor Ayola, and all the professors in the house. Thank you. Please don't be intimidated. Don't worry. We are getting there gradually. And very soon, we will, by the time we are launching into that real world, we will remember this particular training. It is not all about certificates. It is all about what you know. When you get out there, when they throw that question to you, during the interview, during the chats, you know, the beauty about all the